quantum computers are not science fiction. They are real, and they are here. And in fact, I have one right here. I'm going to show it to you in a minute. A real full-scale quantum computer will be, of course, much more grand and way more complex. And yet, a global community of quantum researchers are making solid progress in leaps and bounds every day towards that goal. When they are finally here, they will be incredibly powerful. For example, they will be able to break our current internet security in seconds. While the same task will take even the most powerful supercomputer of today thousands of years. But rest assured, quantum computers are not here just to break other people's code. More importantly, quantum computers will transform how we manage resources, how to design new drugs, how to design new materials, and a million other things we possibly have not even dreamed of yet. So it's important. What makes a quantum computer so powerful and so different from our current day computer? Well, our current computer using binary bits. Those are the zeros or ones, and they work on one number at a time. While quantum computer use quantum bits, namely qubits, which can be representing many zeros and many ones at the same time. Consequently, they will be programmed very differently, and their hardware will work very differently. To explain that, you will all need to learn a little bit quantum physics. Don't worry, you will be okay. You have all heard about the electrons, which are the tiny particles with a round nucleus in an atom. That's what we learned from school. That picture is not quite right. There are times electrons do behave like particles, but that's not their true nature. A normal particle can be at one place at a time. It's like me standing here. I can't be at the same time also standing over there. However, a quantum particle can indeed be at two places at the same time. If you find that troubling, you are not alone, because we know Einstein didn't like it at all. Quantum particles, like electrons, behave very strange. They can be in both places at the same time. So if I have one quantum particle, I'm going to use qubits from now. One qubit here means 0, there means 1. If I have two qubits, it will be 0, 0, 0, 1, and 1, 0, and 1, 1. 4 numbers at the same time. Every time you add one qubit, you double the amount of information a quantum computer can hold and process, all at the same time. And doubling is very powerful. If I have a piece of paper, it has to be very, very large piece of paper. And if I fold it nearly 27 times, the stack will be as tall as Mount Everest. 42 times, it will bring me all the way to the moon. And you can see how quickly a number can become really, really big just by doubling. A quantum computer with 30 qubits can hold 1 billion bits of information and process them at the same time. Is that amazing? Let's apply it to a real problem, such as a traveling salesman's problem. Let's consider a salesperson needs to visit 50 clients in different places. And we want to know which one is the shortest path. It sounds a really simple problem, right? You only need to calculate the total distance and compare them. But it turned out to be a really, really hard problem for computers, simply because the number of possible paths of visiting just 50 clients is astronomically big. So it will take a normal computer forever, literally the age of the universe, to check through all those numbers. And by that time, who cares? A quantum computer are really good at manipulating, processing many, many things in quantum parallel, all at the same time, even that number. A quantum computer only needs 215 qubits to be able to do that. Is that too good to be true? Because there is a catch. The quantum computer knows the answer, and it holds all the information. But we don't. We have to look and measure. If you find superposition weird, wait for this. The moment I measure the quantum state, it collapses into one of the 3 followed by 64 zero possibilities. The probability of that quantum computer give you the right answer, the shortest path, if you remember, is 1 over 3 followed by 64 zeros, literally a zero. Can we somehow ask the computer, say, yeah, please, just give me the one state, which is what I'm trying to find out. Can we do that? If so, how? Interference is another quantum phenomenon. By carefully design a quantum software, we can engineer interference in such a way all the qubits will interact such that the right solution, the probability will be amplified. All the wrong solutions will be canceled out. And then you look, and then you have a very, very high probability to measure the right answer. That's the power of quantum software, and that's not easy, but it can be done. It has been demonstrated to be able to solve a range of problems. I think you all agree the quantum computing is strange. You may wonder what it looks like. Yeah, does it have a keyboard? Or does it use Windows? Or it has to rely on some giant sparks typing through the room, like in a science fiction movie. Right here, I have a quantum computer to show you, and prepare to be underwhelmed. And you can see inside, it's a physical device. And it is, truth be told, it is a real quantum computer. It uses 2 nuclei of a particular molecule to act as 2 qubits. So this machine can think about 4 things at the same time, better than what I can do. Currently, world-leading quantum computing companies are building highly sophisticated quantum computing devices with ever-increasing complexity. Just early this year, IBM built a quantum device which has 1,121 qubits. And it represents 2 to the power of 1,121, which equals to 3 followed by 337 zeros. It's a huge number. It's more than the total number of atoms in the entire universe, and multiplied by 250 zeros. So this leaves us a few questions. Number 1, are we prepared for the impact of quantum computing? No, I don't think so. Right now, there are very few people who actually understand the quantum tricks to make that happen. We need to vastly expand the range of quantum computing applications. I'm leading a quantum software research group in the University of Western Australia, And our team consists of physicists, mathematicians, computer scientists, financial analysts, and bioinformaticians, and even medical doctors. Our mission is to develop quantum softwares, quantum algorithms for a wide range of end users. Question number 2, can we afford to overlook quantum computing? I think the answer is also no. Industries and businesses will need it to keep their competitiveness. Nations will need it for their future global standing. Our world needs it to address challenging problems such as climate change, energy crisis, global health, data privacy. Quantum computing stands as the pinnacle of science and technology. It's a grand challenge of this century. It offers enormous potential for everyone, for us and for our children. Thank you.